So I think so for the problem session today at 3:30, I think we should just meet at like Cardwell 120. It seemed to be open last week, and there were too many people from my office, so we'll just meet there. Write it down. So, problem session. At 3:30. PM. It's like Cardwell 120, and if someone schedules something in there, then we'll find somewhere else to go. But I'll ask the office to reserve it. And of course, so last time some people got on, and I wasn't on, so it may take me a few minutes to get everything, get the meeting started. Yeah. I can hear you. It's my personal links. I think I sent an announcement with it. It's the same one. I'm just going to use my personal room for that. I don't want to set up any. Probably should, but I. So yeah, just go there. No password or anything. Okay. So. So last time we talked about partitions and equivalence relations and their relationship between each other. And this time we want to extend that a bit and talk about, well, maybe not extend it, but apply it really to groups. So what we'd like to do is take a group. We're going to prove this corollary 2.8.3, and kind of some of these corollaries are kind of short, so I'm not going to copy them over. I'll just write them out. So it just says the left cosets a subgroup H of group G partition the group. So recall what a left coset is. If I have an element A in G, then AH, this is what we call a left coset. And it's just the set of all multiples of law of composition being multiplication for this group of where H ranges over all of the elements of our subgroup. We call a left coset. So I'm going to prove this in a certain type of way that sort of does a few of the theorems that corollaries, I think, in the book. Their proof is very short, but then they prove a few other statements, which are different. Before this, the corollary. Okay, so I'm going to define something. I'm going to define a relation. So we'll define relation between elements of G. And I'll call it like congruence with a subscript H on G to be I'll say that two things are congruent. Yes, if and only if A inverse B is an element of the subgroup H. That's going to be my relation between elements in G. Now, what we learned last time is that partitions and equivalence relations are basically the same thing. If I have one, I can get another. And so what I want to show is that this particular relation is indeed an equivalence relation. We'll see that actually we just sort of use the three basic properties of a subgroup to get the three basic properties of an equivalence relation. So claim this is an equivalence relation. G. So what do we need to show? we need to show? The first property. Reflexive. Yeah, so we need to show that something is equivalent to itself. Well, so one sub G is equal to A inverse A, right? For any A. Should have started there. Sorry. We say for any A. And G. Once. But that's an element of H, right? One is an element of H. Identity, I mean. So A is congruent. We just take this expression, well, this condition, if I put B as A, is saying A is equivalent to A by the definition. This establishes that it's reflective. Next, we need symmetric. Right, we need that it's a symmetric condition. So let's assume A is congruent to B. Well, then by definition, A inverse B is an element of H. But H is a subgroup. And so if I have an element of H, I have the inverse of that element. That's one of the three properties, right? So let me call it this. Let me do it this way. B inverse of A inverse. Oops. B inverse of A inverse. B inverse of A equals B inverse A inverse inverse. Sorry. Which equals, well, you know that when you take an inverse of a product, it switches the order, right? So this is equal to A inverse B inverse. As I was just saying, if this element A inverse B is in H, its inverse is in H. Yes.
Your second term there, B inverse, A inverse, is that third final inverse like over B inverse A inverse or just?
No, I just have a parenthesis over A inverse. So it's just the inverse of the inverse. If that, yeah, I'm not, that wouldn't be true if I put it around. That wouldn't be true. I'm just saying that A is equal to A inverse inverse. If I take the inverse of the inverse, I get back to A. That's just sort of right from the definition of what an inverse is. And therefore, applying that B is equivalent to A. With symmetry. And then for transitivity, well, what haven't we used for the properties of subgroups? We haven't used that a subgroup is closed under composition, the law of composition. So let's assume that we have the setup that A is congruent to B and B is congruent to C. Then, well, by definition, A inverse B and B inverse C are elements of H. We can compose them. In particular, we can just look at A inverse C as the composition of A inverse B times B inverse C. This, because the subgroup composition is in H. Giving A is congruent to C. So we do indeed see that we get an equivalence relation, and thus the equivalence classes of the elements form a partition. That's what we showed last time. We have an equivalence relation, the equivalence classes form a partition. This is the proof of the claim And now let's take a look at the equivalence class. Let's claim, I don't know, this claim is kind of silly, but okay. If I look at the equivalence class of A, then this is equal to A times H. Equal to the coset A times H. So, well, to see that, let's just make the argument. Okay, if B is an element of CA, then A inverse B. B is congruent to A, so A inverse B is an element of H. We can just, let's call little h, this is an element of H, or multiplying both sides by A, we get B is equal to AH on the left, which is an element of A. So that says that the equivalence class of A is contained in this left coset. And the converse is almost already written, but reverse conclusion, maybe I should say. If B is an element of AH, then B is equal to A times H for some H. And then we can just multiply by A inverse. Okay. So indeed, the cosets are the equivalence classes, and that establishes this corollary. That the left cosets partition the group. So let's take a look. I was thinking to do this sort of actually kind of walking down here. Let's take a look at an example. That way we can kind of maybe see a little more. Maybe we'll observe something. When we look at this example. So yeah, sorry. Okay. Do people have like a favorite subgroup of S3? Is it too soon? People that haven't like developed preferences for subgroups of S3 yet. So can anyone tell me a subgroup of S3? But one way of finding subgroups is you can always take a cyclic subgroup, right? Just take an element of the group and look at all of its powers. Right? That will give you a subgroup, whatever it is. So, and indeed for S3, we can do that really, those basically every subgroup that's a proper subgroup, namely it's not the whole group or the trivial group, is of that type for S3. So I could take, let's do, we'll do this example. We'll take 1 and we'll take 1, 3. I take 1, 3 and I square it, I get 1, right? I switched an element, right? It's just switching 1. This is my subgroup. This is my H. Now I want to look at the cosets. Okay, I'm going to look at the cosets. So to look at the cosets, because I'm writing things to look at the left cosets, there is a notion of right cosets, which is what you think it is. You just multiply everything on the right. Okay. But if to look at the left cosets, I probably should highlight these on the column in the Q side. This is my group 1 and 3. Now, what are the cosets going to be? Well, I can just look at this table and I can look along these 2 rows. And for each column along those 2 rows, I'll get a coset. The one coset I'll get is just the subgroup itself. I won't multiply the subgroup itself by 1. I'll just get that subgroup, right? Every element will just be that subgroup. So I'll just get that and that. But it's funny, there's another coset that is also H. It's also the subgroup in this case. What is it? what other way can I write a left coset that also gives me H? I'm looking for things like A times H, which means I'm going to look, I pick an A out of one of these guys, and I'll look in the column, in these two columns, and I'll try to see what I get. That will be my coset, my left coset. What else? 1, 3. 1, 3. If I look at 1, 3, I get these two guys. Right? Why is that? Because 1, 3 is in the subgroup. And so it's closed under multiplication, right? So I'm just multiplying the elements of that subgroup by something in there that's just going to permute those things around. Elements around. Those are the only two that give me H. So what about 1, 2? Well, 1, 2 will give me 1, 2, and 1, 3, 2. Is there any other element that gives me 1, 2, and 1, 3, 2?
1, 3, 2.
1, 3, 2. If I look at the remaining two, 2, 3, I'll get 2, 3, 1, 2, 3. 1, 2, 3 gives me 1, 2, 3, 2. So what I see when I do this is I see that the partition breaks me, is breaking me up into these three colors: the red, the, I don't know, is that orange, orange, and the purple, right? So those are my equivalence classes. These are the cosets. Now you'll notice something when you look at this, which is maybe kind of obvious because of the way we set this up, but it's true in general. The number of elements in each of the cosets are all the same. There's 2 in each of them. Of course, that number is equal to the number of elements in the subgroup, because the subgroup itself is a coset. So that's actually a theorem, or corollary. Lemma. Something. Lemma. And this holds for cardinality, not just, in other words, if it's some infinite thing, it's cardinalities, that there's a bijection between these two sets. So how do you think that works? How would you prove something like this? For any element of the group. Yeah.
Show that there's a homomorphism or an isomorphism.
So this is, you can do something like this. Well, so let's be clear about something. These cosets are not groups in general, not subgroups in general. If I take the red one, this is H, so it is a subgroup. But if I look at any of the other two, or in general, any of the other ones, these aren't groups. If I square this, I get 1, right? And that's not in that set. And if I square this, I get 1, it's not in that set. So these cosets are not actually, they don't have this kind of law of composition contained within themselves. Now there is something we can do sometime, and we'll get to that in a bit, maybe next week. But for now, the algebraic structure of these things is not so clear. They're just, we should look at them as just sets. We should look at them as just sets for now. So if I have 2 sets and I want to say that they have the same number of elements in them, what do we do? How do we do it? How do we show that? How do you show? Huh? I couldn't hear you. Count them. Okay, but what's like the fancy way of saying that? how do you count in fancy math terms? What's the fancy? Huh? Oh, well, this, okay, so this is the notation of the cardinality, right? Yeah. But what do you need? What is the mathematical definition to say that 2 sets have the same cardinality? You need a bijective map. You need a 1-to-1 onto map. And you said count them. That's what bijective maps do, right? They say, okay, here's a set of numbers, 1 through whatever number you have, like 5, and here's a set of coffee cups. Get a bijection, you know, and that's, you know, that's, but there's that term, and we want it so that we can use it in proofs. And for this, we can all see the bijection, I think. We'll see. I'm going to get a bijection, and to see whether I have a bijection, sure, you can prove 1-to-1 onto, but it's easier, especially in groups, to just show you have an inverse function. So I've got 2 sets, H and AH, and I want to give myself 2 functions, one from H to AH, one from AH to H. I want to compose them and say that's the identity. So how do you think I'm going to go from H to AH? Take a wild, well, don't take a wild guess, take a guess. Oh my gosh, multiply by A, right? Amazing. So we're going to do A, and we're going to multiply whatever element we have in H by A. How will we go to AH, remembering that we're in a group? I mean, that A is an element of a group.
We divide.
Divide. Don't say divide. I hate divide. Multiply by the inverse. I know it's the same thing with multiplicative notation, but use like inverses. And the reason for that is, well, there's a reason. Reason for everything. Not really. Okay. These are the 2 maps. So in other words, if H is in here, I send it by my function to A times H. I have some A times K in here. I send this to A inverse times it, which is just going to be K. And you can quite clearly see that if I start here and go here and then come back, I'm multiplying by A, then I'm multiplying by A inverse, that's by the then, and vice versa. So this is an inverse pair of functions, and therefore these are in bijective correspondence. They have the same number of elements. And when I say that, again, if it's infinite, that means they have the same cardinality. How many people know about like cardinality in the infinite setting? Yeah. So it really makes me feel very mournful. But I don't know. I mean, if this is your first kind of, so it's a really beautiful and really amazing kind of thing that takes a minute to digest, I guess. It certainly was not digested by the mathematical community at the time. There's this guy Cantor, who kind of had a lot of crazy ideas, and this was one of them. Yeah, very, very much not loved by his peers at the time, and ended up kind of going crazy and killing himself. So that was sad, but he was like very brilliant and had wonderful ideas, amazing, like a whole set of beautiful, interesting ideas.
Why are all mathematicians have super sad stories?
That's not true. You know, there's like cool mathematicians that aren't crazy. There are a few. I know one.
But like
One
the
or two.
big
I'm
ones.
cool.
Like the real big ones, they got sad stories. Like
They don't all have sad stories. That's nonsense. I mean, think of Gauss was like the great, right? I mean, Gauss, he didn't have a sad story. He was like a cool guy. I mean, he was super cool. Like he was progressive. You know, there was like Sophie Germain, a woman mathematician. Who's like, I don't care what gender she is. She's just got good ideas as a publisher. He's a good guy. So, you know, there are guys like that. There are a few guys like that. A few ladies like that. Noder was awesome. She was great. She did die of like something. A lot of people died. I mean, people died. I mean, back then it wasn't fun. You got some sickness, you broke your leg, you're dead. So 100%
of people die.
Yeah. So yeah. Anyway, his result. I mean, a very simple result, which is you can prove exercise. If you have a set S, you can construct something called its power set. Power set. This is the set of all subsets. This is just an aside, but you guys should all know this. The set of all subsets. So it's all subsets of S. You can prove just by contradiction that these do not have the same cardinality. there's no bijective correspondence from one to the other. Awesome. It's a really, you can kind of try it. You might come up with a, well, it's a little bit tricky, but try it. It's fun. And if not, you can probably find it on, online easily. It's a really neat proof. But it shows you that there's no bijective correspondence between, like if you take an infinite set, its power set is also infinite. So there's no bijective correspondence between these two sets. So you have actually, like the sizes are different. One is strictly larger than the other. One's strictly larger infinity. That may not shock you, but it should shock you because there are a lot of sets that you might think that are infinite that you might think are different cardinality, but are the same cardinality. Like you take all rational numbers, that has the same cardinality as all like numbers 1 to infinity. So countable set. So it's kind of interesting that you have these different orders of infinity that live out there. But this lemma is saying that if we are looking at groups and cosets, even for infinite sets, you have the same cardinality for cosets. And there is some caretaking in Artin to prove things even in the infinite context. And there's a reason for that because some continuous groups and infinite groups are studied, and you want to have some theorems that apply to all groups. All right, so let's get back to groups. So there's notation for this particular partition of a group by the left cosets. So rather than writing G over the equivalence relation that we just write, the notation, this is definition maybe. So we write G over H for the partition, well, I'll just say for the set of left cosets. So this is equal to all of the left cosets, left H cosets, I guess. And we take pi from G. We call this usually the quotient map, at least in the context when we have a few more conditions on H. We also write G, this is kind of strange notation. This notation is something that's, although it's sort of set in stone, for the cardinality of this partition. So the number of left cosets. We call this the index of H and G. That's the word. So if it's, yeah, so that's what it is. Now, let's prove Lagrange's theorem. Lagrange is also probably not crazy. Probably, you never know. You guys been to Paris? So you go to the Eiffel Tower. Along the base of the Eiffel Tower, they write all of the names of like the great French mathematicians and scientists. So you'll see Lagrange on there. That's a country that knows they love their mathematicians. Of course, they have a wonderful history. All right, so Lagrange's theorem. So if we have a subgroup of G, H, and G is finite. So, like I mean, think of symmetric group, think of the cyclic, finite cyclic group. Well, there are many others, but we'll run into a few of them as we go, like rotations or symmetry group or something. And G is finite, then H divides the number of elements in H divides the number of elements in G. And furthermore, I mean, we have an equation. But in fact, the number of elements in G is equal to the product of the index with the number of elements in H. We can reread this equation by the definition of index is the same as the following, which is if I take the set of left cosets, I take its cardinality, this is equal to this question. This is what I was trying to say a while ago about understanding certain shadows that you can see in math, is that, you know, there's these kind of complicated constructions like sets of cosets, partitions, equivalence relations, and so on. And we construct them, but then if we do something as simple as count the number of elements in that set, we start seeing kind of some arithmetic in our notation that translates over naively. You know. Yeah.
Can you explain again the index?
So it's just, yeah. So the index is just, oops, the index is, what just happened? The index is the number of left cosets. So in this example we looked at, the index of this subgroup here is 3, because I have 1, 2, 3 left cosets. So it's just, it's the number of left cosets, that's it. But it's this notation because, well, it's meant to agree with other notation that you encounter in Galois theory. It's the actual set. So the index is a number.
It's like, is it like left cosets of the form like AH?
Yep.
Okay. Yeah.
That's the only
It just sound
form.
like you meant all.
Left cosets of H, yes, is what I'm
Okay.
referring to left cosets
Yes.
of us. So I'm fixing the subgroup H.
That makes a lot more sense.
Sorry. So let's prove this. Not hard. Well, okay. Yeah, this is not hard, actually, just generally. Let's just prove it. So all we have to do is use our lemma, the lemma that was written up here, which said that the cardinality of the left cosets are all equal to the cardinality of H. So the number of elements in each left coset is equal to the number of elements in H. And then we just have to realize we have a partition on it. I'll just say since these guys form a partition, that forms a partition of G. This is what we proved the first thing in class. We have that G, it's as a set, is equal to the disjoint union, symbol for disjoint union, of all of the left cosets. A partition is saying that I've got a collection of subsets which are all disjoint, all non-empty, and their union is the whole thing. So I'm just writing this out, saying this is a disjoint union. But what that means, since G is finite, is that the number, if I count the number of elements in G, I just have to count the number of elements in each of these cosets and add all of them up. This is equal to the sum H in G over H, number of elements in AH. But by our lemma, the number of elements in AH is the same as the number of elements in AH itself. Is equal to the sum. For every left coset, I have a copy of the number of elements in H. So I'm taking the single number, the number of elements of H, and I'm adding it to itself for each element of the left cosets. So that is equal to, I just multiply by the number of elements, number of left cosets by the number of elements in H. There is a left coset for every element of H, but it's not unique. So I don't want to sum over every element in G and take the left coset because I overcount. because as we saw before, when we have two elements that give us the same left coset in that example we calculated. Just want to take each left coset and do that. Interesting. Does that make sense? I'm taking each of the left cosets and I'm taking the number of elements in that. I'm adding them. So how many left cosets are there? Well, there are this many left cosets. And that's equal by definition to the index of H and G times H. And that establishes the, here, that's it. Lagrange's theorem. So Lagrange's theorem, as innocuous as it looks, is it's just really powerful. It gives us a lot of information, So for instance, let's look at some simple applications here. Let's say you're interested in S5. You should be. Yeah, so the S5 has this group inside of, you remember the alternating group, right? It was the kernel of the sign map. So that is, so if you look at the alternating groups, A2, A3, A4, they're really exceptional. This happens in group theory, actually. When you have low numbers of elements, you get all kinds of neat little things happening, and they're special. This also happens in topology. So like if you're studying spaces, in low dimensions, very hard and interesting things happen, and then higher dimensions, everything becomes easier. It's kind of weird. At least in some sense. But once you hit 5 for the alternating group, you have what's known as a simple group, and it's a non-abelian simple group, and it's kind of the first of its type. And yeah, that's exactly right about the quintet. That's exactly why the quintet. Anyway, applications. So let's say you're interested in S5. So we can say something. This is just a silly application, but let's say. So how many elements does S5 have? You guys can tell me. It's at 120. That's true. 5 factorial, right? So there's no cyclic order 7 subgroup or 11. Everyone see why? Everyone knows? How many elements are there in an order 7 subgroup? 7. It's 120 divisible by 7. No, it's not. So if you don't have Lagrange's theorem, you're going to take a long time to try to prove that. I mean, probably not too long, but long enough. You don't want to spend that time. Lagrange's theorem says you just have these numbers you can deal with to get immediate results. Let's look at a far more powerful application, which I think is a corollary. So suppose I have a group G of order P. Or some prime or prime number. What can you guys tell me about that? Here? Okay, you can partition it. You can partition anything you want because partitions are set statements. But you can't partition it in the way we've been partitioning today, right? That's why I think you're thinking, at least not non-trivially. Why can't you do that? Lagrange's theorem. Well, okay, so what in particular about primes is something you guys know?
They're only divisible by themselves in one.
Yeah, this is like the biggest, the worst definition ever, but it's okay. Think about that later. It's true. They're only divisible by one in themselves. So in other words, there's no non-trivial subgroups, right? But a non-trivial subgroup, trivial subgroups are of a group G are the identity and the entire thing. That's how you call it, what you call trivial subgroup. You can call, if you have a subgroup that's not one of those two groups, then you call it proper subgroup. I can say there's no proper subgroups of this group. Because if there were, a prime would be divisible by some number other than one in itself. Right? Okay, that's kind of curious. Can't you, I think we talked about subgroups. Can't we always find, like earlier today, we said, how do we find subgroups of S3? What do? I give you a group and I say, hey, give me a subgroup of that group. What are you guys going to do? The memory test. Short-term memory.
Ask the question.
Reminds me of my advisor when we always have to, like, our advisors have to watch us teach when you're in grad school. Here we have teaching advisors. You have to get evaluated on that. He's like, it's like, your lesson was great. You did a really great job, but your voice, the tone of your voice almost put me to sleep. So monotonous and boring. Don't spare my feelings. So sometimes when I get like these reactions, I'm like, oh gosh, I got to put a little more intonation. Okay, let me try again. How do I find a subgroup of a group? I give you a group, any group I want. I've got all kinds of groups in my head. I give you one group and I say, produce for me a subgroup of said group. What is one thing you can do to give me, aside from giving me, the trivial groups, trivial group of the whole group? What is one thing you can do to produce a subgroup of that group? There's no positives. What is a positive? What is a positive matrix? Nobody knows. Groups are abstract things. It's a set of things, right? They have a law of composition. Maybe you're on something, you take an element. Choose an element. Yeah, Tim. Yes, exactly, right? Take an element, G or A, whatever you want to call it, and take its square and take its cube, right? Keep on doing that. It goes on forever, then it goes on forever. So what? You got it. But then you take its inverses, right? And you take all of those. That forms a cyclic subgroup. If you have a group, you choose an element, you can always form a cyclic subgroup. Just take all of its powers in just multiplicative notation, right? Or an additive group, take all of its, n times all of the integers. Always doable. Give you a subgroup. That's what we did with the symmetric group with S3. We just chose an element, we took a square, we saw with identity. We're happy. Okay, now I have a group G of order P. I take a non-trivial element, non-identity element. I take all of its powers. What do I get? Have to get G. I have no proper subgroups. It's prime order. I have no proper subgroups. I have to get G. So what does that tell me G is? G is cyclic. G is cyclic. Very good. G is cyclic. So if it has prime order, it is a cyclic group. And not only that, every single element that is not the identity is a generator of that cyclic group. That's pretty cool. G is cyclic. In fact, G is equal to A for any A not equal to. So we have done something already, which starts a long process of mathematics, about 100 years of mathematics, right, which ended, as I said, kind of only recent. I mean, I'm not sure it's ended. Some people are clinging on for dear life. We classified a collection of groups. We classified it. You tell me you've got a group of prime order, I tell you what it is. It's a cyclic group. I know all about it. It's a cyclic group. Of course, once you get past order, I mean, you can say that about a couple of things, but actually, once you get to order 4 groups, first non-prime, you already have 2 different types, non-isomorphic groups. When you get higher, you have like there's of a certain order, like 12 or 24 or 60. You have a lot of different groups that you can consider, a lot of non-isomorphic groups. So there's a lot of interesting things going on in groups that are composites. Right? They don't all break down into primes. They're more complicated than that. And that A5 is sort of an example of one of those fundamental kind of groups that people are interested in. Okay, so this was a corollary in art, but it's something to keep in mind. It's actually really useful. And in fact, we see that this group, order P, so it's cyclic, it's abelian, right? Cyclic groups are always abelian. Order prime, if we just look at that group and write it additively, then we can start building even more algebraic structure on top of it. And really, they're really actually important and interesting groups, interesting algebraic structures. We'll get to that. Okay. So there's also this proposition about the multiplicative property of index. I'm just going to write it. And I'll say note, you should read this section carefully. This is not a hard thing to prove at all if you assume that G is finite. This just follows immediately from Lagrange's theorem. However, you can have infinite groups with finite and subgroups with finite index. So you can actually prove this just for finite index subgroups, even when H, G, and K are all infinite. This can still hold. You can still have finite. So an example, what I was just saying, not of this. I want you to read about that in the book, but an example of this is you can consider the additive group of integers. And consider the subgroup. Well, let's do 3. In fact, we're going to talk about this more on Monday too. BC. Remember, the plus there denotes that we're talking about addition. It doesn't mean positive. And I know that's confusing, but that's just so this is a subgroup, right? We showed that this is a subgroup. In fact, all groups are kind of something times E plus. All subgroups are. Now, what are the cosets? So this is an additive group, so I'll write a coset like A plus. I'll use the operation of the group. What are these things?
It's all just it's like
modulus
shifted.
something nonsense.
Okay. Nonsense. Come on.
Just like the thing where it does like all the modulus of like 3 or something.
All of cryptography nonsense.
Yeah.
Okay, well,
It's counting by keys.
tell that to the military. Disagree.
But it'd be like 1, 2, 3, but then it would like loop back to this like
Right. So, okay. So let me, instead of giving you A, let me give you something more concrete, like 2. So if I have a number in here, I'm going to write down what this is. These are all numbers, all integers that have remainder 3. sorry, remainder 2 when divided by 3. So, I mean, let's just take an example. Let's say we have 11. 11 I divide by 3, I get remainder 2, right? So that means that 11, why did I write H? What's going on? That means 11 is equal to 2 plus 3 times 3. That's an element of here. Of course, you can see that that's true for any integer that has remainder 2 and you divide by 3. I can do something like that. It's 2 plus 3 times. I can put it in here. So all of these, and the picture that was, I think, being illustrated there is you can write out your integers. Okay. Do this, and I'll go down a little bit. And you can look at sort of, okay, you can look at this at the numbers that are divisible by 3. Right? And then you can shift that over 1. And those are all going to be the numbers that have remainder 1 when you divide by 3. So if you shift it over 1, you'll get this guy. These are all the numbers that have remainder 1. And if you shift again, you get all of the ones that have remainder 2, the one we're just looking at. And you can see that that is all those are going to be all of the cosets you get. Except 3, because when you divide by 3, you're going to have a remainder 0, 1, or 2. That's it. Those are the 3 cosets you get. So this does lead into modular, they call modular arithmetic. But anyone who's programmed, I'm sure has seen this, right? You have this, like, how do you add and multiply mod a number? This is sort of the algebraic way to express modular arithmetic as left cosets. That's the correct way of talking about it. Okay. All right, guys. I think I'm at time. So please look over some problems, bring me some questions for the problem session. If you join online, that's fine too. You can just ask online. But I look forward to seeing you all then.